Welcome to the UMBC webinar, Engineering the Census, Systems Engineering on the 2010 Census Program. Our guest speaker, Fred Highland, will begin his presentation in 5 minutes. But before he starts, I'd like to give you a brief overview of UMBC's graduate programs in Systems Engineering and Engineering Management. Both of these programs were designed by industry experts and are taught by highly experienced practitioners who want to help students prepare for successful careers. They consist of very practical courses to give you the skills you need to advance to higher levels of responsibility in your company. One of the advantages of the UMBC programs is their flexibility. You take 4 or 5 required core courses to learn basic skills, and then you have the flexibility to take the remainder of the 10 courses from many choices. The schedule of courses is flexible too. The courses are taught 2 or 3 times each year in the evenings, and many courses are 50% online and 50% face-to-face. Our Systems Engineering program began in 2004 in response to a request from Northrop Grumman for UMBC to create a technically oriented program to teach engineers the fundamentals of systems engineering to accelerate their careers. Usually it takes 10 years or more to learn enough about systems engineering to be in a responsible role in your company. But by learning the fundamentals, you can become a successful systems engineer much sooner. There are 5 different graduate programs at UMBC involving systems engineering. The first is a certificate program in systems engineering that requires 5 core courses in the fundamentals. These same 5 core courses can be applied to a Master's of Science in Systems Engineering, where you take the core plus 5 electives. Or you can take the same 5 core courses and 5 or 6 courses in electrical engineering, computer science, or engineering management to get a Master's of Science degree in those fields with a systems engineering track. Here are the core courses and electives required for the Masters of Science in Systems Engineering. The 5 core courses cover the system engineering life cycle from system concept through the requirements definition, architecting a successful system, modeling and simulating it in advance of building it so that you can be sure the system you're designing will actually do the job, and then building, integrating, and testing it. And the final core course is a capstone project that uses what you learned in the 4 previous courses. Teams of students choose a complex system to design, model, and simulate. The remaining 5 courses in the master's program can be taken from several different engineering disciplines, depending on the field that would fit your career the best. This is a summary of the benefits of the UMBC Systems Engineering program. The flexible curriculum is designed to fit your career needs and interests. The curriculum was designed by system engineers to provide focused knowledge and skills for success in your career. The faculty members are subject matter experts with many years of experience. The courses are rigorous and focused on the skills you can use immediately in your workplace. And the courses are at convenient locations and times for work-life balance and to accommodate travel. You can explore the details of the system engineering program, including the courses, the faculty, and the schedule at the Systems Engineering website, which is umbc.edu/SE. Now let's take a quick look at the Engineering Management program, which combines 6 practical management courses with 4 technical courses that provide depth. Most of the management courses are 50% online and 50% face-to-face, so that for each course you come to campus only 7 times during the semester. You take 4 management courses that apply to either a Master's of Science degree or a certificate, 2 elective management courses from a list of 14, and 4 technical electives chosen from 10 technical tracks, including system engineering and cybersecurity. Here are the 4 core management courses. You take either one of 2 choices of project management. One is a general project management course, and one is aimed specifically at systems engineering. You take a course in management, leadership, and communication, a course in law and ethics, and one of two choices in financial management. One of these financial courses deals with company finances, such as cash flow and balance sheets, and one deals with the financial decisions managers need to make during their normal workday, such as investing in new technologies or new facilities. And in addition to these 4 courses, you take 2 management electives and 4 courses in the technical tracks listed on this next slide. There are 10 technical tracks covering most of the engineering and IT disciplines, including systems engineering and cybersecurity. You can take courses from a single track or courses from several tracks. This flexibility in technical courses allows you to obtain breadth in technology, and it's very popular with our students. I invite you to visit the engineering management website, which is umbc.edu/engm, to explore the program and these courses in some detail. And if you have questions about either systems engineering or engineering management, you can ask them during the webinar by typing them, or you can contact me or the other persons listed under Contact Us on the webpage. These slides and the main presentation will be available on both the System Engineering website and the Engineering Management website in a few days. Now let's begin the presentation on the 2010 census. I'd like to introduce Fred Highland, a colleague of mine, who is a senior fellow at Lockheed Martin and quite an expert. Welcome, Fred. I'm going to hand over the presenter role to you now.
Thank you, Ted. I'm going to describe a use case for system engineering based around the 2010 census to show you the kinds of things that system engineers do in real-world large-scale problems. But first, a little bit of background. Ted mentioned that I'm a senior fellow with Lockheed Martin. As part of that role, my primary responsibility is to be a system architect on various programs to define large-scale solutions to various customer problems in the government for the U.S. and other countries. In particular, for the last 16 years, I've been working on census solutions, beginning with the 2000 U.S. Census, and also doing the architecture for the 2001 UK Census, the 2006 Canadian Census, and actually developed the architecture and advised on the implementation of that for the 2011 UK and Canadian censuses. But I was also the systems architect for the US 2010 Census DRIS program that I'll describe, so that's where my background really comes from. What I'm going to talk about first is what really is the decennial census, what's the motivation behind it, and the challenges that it brings. Then I'll give you an overview of the specific system that I worked on, the Decennial Response Integration System. Then we'll get into specific DRIS system engineering activities. There was a lot of different activities. DRIS, you'll see, is a very large and complex system. It took us over 5 years to actually implement, but I'm going to hit some of the more interesting areas, focusing on system engineering. Then we'll talk a little bit about the results and some best practices from that activity. The biggest motivation for the census is actually the U.S. Constitution. Right on the first page, if you look at it, Article 1, Section 2 says, representation and direct taxes shall be apportioned among the several states which may be included within the Union according to their respective numbers. The actual numeration shall be made every subsequent term of 10 years. That establishes that the Census Bureau or the appropriate agency needs to count the number of people in the country every 10 years for purposes of taxes, for purposes of representation, and for the general economic benefit of the country, to decide, for example, where are we going to put the next Walmart, or do we need more roads, things like that. To summarize it in a different way, former Deputy Director of the U.S. Census Bureau, Jay Waite, put it very crisply. count everyone, count them once only, and count them in the right place. So that really brings out the points about getting it accurate. And also the idea that the Census Bureau really cares who lives where. They want to know how many people live at a specific residence or dwelling in the country, so that they can roll those numbers up into how many people live in towns, states, etc. They actually don't care about the individual, you as a specific named person. They care about where you live and how many people live there, because it's really about what are the demographics of the country that we can then use to plan for the next 10 years. So it is kind of interesting that this is a system that's actually mandated by the Constitution. That's a pretty high-level law to try to meet the needs of. The challenge here is really one of volume. We must integrate the responses from census forms and phone calls. There's an estimated about 115 million households in the United States, about 310 million people. That translates into 110 million mailback census forms, and then another 65 million what we call non-response census forms. Normally your form is mailed to you. Many of you probably received it in the mail. Most of you filled that form in and sent it back, but just under 30% of the people that got mailed forms didn't mail them back. And then the Census Bureau, because they want to count everyone, has to go out and get the information for those people, and that's the non-response operation, which involves a large force of field staff going door to door to get the information for those people that didn't respond. The time frame is also challenging. We're given the challenge of processing the mailback forms, 110 million of them, in the first 90 days of activity, basically from March through the end of May. And then the non-response follow-up in the second 90 days, which ended approximately, well, really the beginning of September. The challenge here is Census Day is April 1st, and we have to collect the data, compile the numbers, give them to the Census Bureau, who then does a lot of statistical analysis and massages the numbers so that ultimately the final number of how many people live in the country is on the President's desk by the end of December of the census year. So that's the ultimate challenge. The forms themselves, the example is here of the main page of the main form that many of you actually received, actually came in 69 different types, different languages. The primary form was, of course, in English. There was also a Spanish form. There was a number of variants of it used by enumerators, used for many, many special cases. It was typically in an 11 by 25.5 inch format, which is really like 3 normal pages tacked together into one sheet. But there were some in standard 8.5 by 11. If you look at it in terms of how much paper was actually processed, it was just over 500 million sheets of 8.5 by 11 standard paper. That's a lot of paper. As I mentioned, you want to get the data accurately, so we had accuracy requirements. A lot of the responses were in what's called marks, check boxes. Those had to be 99.8% accurate. The characters, the written-in answers, particularly things like your date of birth, and that type of information, need to be 99% accurate, and from automated recognition. And then anything that operators had to key still had to be 97% accurate. So they're trying to get very high accuracy to make sure the data is good. And I mentioned everything needed to be delivered to the Census Bureau by September 9th, 2010, so that they could do their final processing and deliver the data to the President by the end of the year. I have a graph here that really represents the challenge that I used quite a bit. This is an engineering activity, so graphs and numbers are really important. You can see at the beginning of this graph this big peak. That's actually the peak mail receipt day, just past the middle of March, where we could be expected to receive as many as 11 million pieces of mail in one day. So we had to build the system to support that kind of response, because it was very important that when we get mail, we check it in and identify who had responded so that we know that we don't have to go ask those people for a response. But during March was the major response period, because the forms were actually sent out towards the beginning of March, and people tend to get the form, fill it out, and respond right away. But that lags as you go through time. There are also a number of critical dates along the way that we had to meet. The first was what they called the Receipt Zero Backlog Day, which was towards the middle of April. And what that is saying is all the mail that came in, we could no longer have a backlog of checking that in. We needed to be able to check it in the same day it arrived by about the 10th of April. And that, again, was to support the non-response activity and encourage response, because what the Bureau was doing with that data was now able to tell which areas are responding appropriately, have high response rates, and which areas didn't. They could use that information to go encourage towns, cities, municipalities to improve their response so that they got properly counted. There's also a Zero Backlog Mailback Day about the end of May. What that was is we had to have processed all the forms that were mailed back up to that point by that day. And that again supports a similar activity of non-response follow-up, because you could send your form back, but we didn't know if you actually filled it out until we opened the envelope and processed it. We could read a barcode through it and find out that you'd actually sent something back, but you could have sent it back blank, or the information, you know, could have been significantly missing. So we wanted to process those mailback forms by the end of May so that we could figure that out and use that information to drive the non-response activity, which followed in June, July, and August. So everything beyond there was largely non-response information, where we took the list of people who actually didn't respond, we didn't have data for, tasked the enumerators to go out and find those people and get their responses and then process that information. With, of course, the final date being due towards the beginning of September, with all the data being sent to the Census Bureau. Now, what you don't want to do in a system like this is build it for the peaks, because the peaks are quite extreme. What you want to do is buffer the data, take all those mail receipts, put them in a warehouse, and then work them off over time to make efficient use of your people and equipment. So that meant continuous processing of approximately 3 million forms every day throughout the first 3 months of the operation. We also had a telephone activity to support. In the early phase of this, it was for help and assistance. People would call up and say, I didn't get a form. How do I interpret this question? Do I have to fill out the form? Many different things, you know, any questions they'd have on responding to the census. The later part of the census, though, after April, gets into what's called coverage follow-up, where we would find forms that the data didn't seem to be complete, and we try to call those people up and get the information from them. That actually involved a lot more activity. A lot of people aren't home, they're not available, you have to call them back, so it's a lot more calls. Millions and millions of telephone calls, up to 700,000 calls had to be made per day. So that meant setting up contact centers to actually address this problem, adding to the complexity of the overall system. So with those kind of numbers and requirements behind us, let me talk a little bit about what the Decennial Response Integration System actually did. This picture is actually from the Census 2010, the Census Bureau's 2010 Enterprise Architecture. It's their view of the entire census process. And it looks like a lot of lines, a lot of connections, looks complicated, and it is moderately complicated. But I always tell people that the census is simple. You basically establish where are you going to count, where are the addresses where all the people live that you then need to send them forms, actually collect the information from the population, and then provide the results to the people that use the census data, the government, the Congress, as well as individual people and businesses. Where DRIS fit into this was kind of right in the middle. Our job was to collect the information from the mail, the U.S. mail, all of the responding forms, to talk to the various other systems in the Census Bureau to provide the status of that information as well as get expectation information, to provide that information to their field operations so they could do non-response follow-up, and to provide the actual response data back to the Census Bureau so they could process it into the ultimate results and provide it to the government and to the country. So we really sit at the center, integrating the data from whatever sources and then providing data and status to the other components of the Census Bureau to do the census job. The overall architecture of DRIS is broken out into a couple of different components. Two major elements, what we call capture and integration. Capture is composed of 3 different segments, each of which focus on a given response channel or response mode. Most respondents were done in paper, so the paper capture was about scanning forms, optical character reading the data on them, validating it, handling a lot of paper. The telephone operation was completely different. They did collect some census demographic information. Most of what they did was provide assistance and provide and call people when they didn't, when their information seemed inconsistent for follow-up purposes. And then there was interactions with the field operation as well. All the data from all 3 of those was integrated together by 3 different segments. One was called Enterprise Data Management, which was about collecting all of the response information, standardizing it, storing it, editing, forwarding it to the Census Bureau. There was also a production data management component that's about managing this entire enterprise, keeping all the management information so that so that the operation could be run efficiently and problems could be identified and resolved. And then finally a system management component that of course just keeps the system healthy and running, keeps the computers going. The ultimate output here, of course, is response data to the Census Bureau, and everything was managed through the DRIS portal, watching what was going on in terms of the system health, security, quality, schedule, and making sure production goals were met. Physically, DRIS was distributed across the country. This is, as I said, very large system that has many different components. We had a major center in Greenbelt, Maryland, where we did some of the central operations, had part of the telephone operation, particularly the central support and control for the telephone systems, and what we call the OCC, the Operations Control Center, that was kind of the war room that ran the whole thing. We had a data center in Phoenix that did paper processing and had backups for our central data control, workflow control and management, and the telephone operation. We had a data center in Baltimore that only did paper processing. It did approximately 40% of the paper processing. Phoenix did another 40%. And there was actually a third center in Jeffersonville, Indiana that did the other 20% of the paper processing. There were telephone switching centers in Denver and in Phoenix that controlled the routing of telephone calls, the millions of telephone calls that were going in and out of this system, making sure that your call got to the right operator or the right place that could service your needs. And of course there were call centers distributed all over the country. We employed approximately 8,000 people in call centers, and most of those call centers were between 50 and 250 people. So it's best to distribute them everywhere so you get around issues about time zones and things like that, because this was effectively a 24-hour operation, although most of it occurred in about a 18-hour period, because the U.S. covers quite a few different time zones. The most physical part of this and what interests people the most is really the paper processing. That is what we did most of. That involves a number of key operations, including sorting the envelopes using very large-scale mail sorters. These things were about 35 feet long, could handle envelopes at a rate of over 20,000 envelopes an hour. basically sorting them out, reading the barcodes on them, and partitioning them into various categories so that they could be processed efficiently. Then the forms had to be taken out of the envelopes and prepared for high-speed scanning. We employed a collection of high-speed scanners that created images, very high-quality images of all the forms at a very high rate of speed, on the order of 12,000 an hour per scanner. And then that paper had to be managed into warehouses for final disposition. Once the images were captured, analysis could be taken on the quality of the image, automatic character recognition performed to try to read the data. Any data that couldn't be read was corrected by operators, and edits were performed to make sure that the data was good. And all that ultimately was stored in our central workflow control and management system. Let me talk a little bit about the real system engineering activities that happened in DRIS. System engineering is defined by NCOSE as an interdisciplinary approach and means to enable the realization of successful system. It's really about doing all that analysis work and the background activities that needs to be done to make sure that the system is successful. It's one thing to design it and implement it, but you need to have the numbers to support it, to know where you're going to get into trouble, to know how big it's going to be, how big it needs to be, and all those things. That's what system engineering is really about. And along with that, what really is a system? And I like the NCOSE or the ISO definition of systems, that there are quite a few others around. It's basically a collection of components and their relationship to each other. And a component may be hardware, software, humans, processes, procedures, facilities, even naturally occurring entities. So it isn't just hardware and software. It's the processes that go with it. It's the people that operate it, the procedures they use, the facilities. And we dealt with a lot of this in the DRIS system that makes it really interesting. Now, modern systems development isn't quite like what it used to be. Most of the time it's now what we call COTS intensive, computer off-the-shelf components. You can buy hardware and software systems that do many of the things that you need to do in most systems. So hardware, to a great extent, has become commodity. You can buy servers, workstations, all kinds of stuff. It doesn't require the level of hardware engineering that it used to. You can buy it off the shelf or from large companies like Dell or IBM that sell these kinds of things. Even the software has the same characteristics. You can buy software that does many of the functions. For example, optical character recognition seems like some sort of AI technology. Well, you can buy software to do that. There are many packages out there. But somewhere, all of these packages need to be integrated together. They need to be configured to do the job you want, and that's where the work really is. So the system engineering task in COTS-intensive systems is much less focused on electrical and mechanical engineering as it would be in, say, building a fighter jet or something, where there's a lot of aerospace engineering, mechanical engineering that have to be done, and much more on making sure the software integrates and performs, making sure the overall system and the hardware and the software and the people integrate together and perform to the requirements of the system. Just taking a look at system engineering processes, this is another reference to NCOSE. This is the list of processes they see behind system engineering. And I just went through and said which ones were major activities in DRIS. And you can see almost all of them have checkboxes next to them. Those are major things we had to do and the system engineers had to do to make DRIS successful. Even the ones with the red X's, things like electromagnetic compatibility and environmental effects, mass properties. We actually had to do some of that in DRIS, but it wasn't a major effort as it would be in a system that was not as COTS intensive. But this is typical of what you see in modern information technology systems. I also have to say that the system engineers were involved at all levels of program operation. There's an overall weekly, monthly reporting cycle that these systems operate on, what we call business rhythms. There's a central meeting of called the DRIS Independent Product Team. that brings together all of the aspects of the system. There's cost meetings, there's risk meetings, there's program management reviews, and senior leadership meetings. The system engineers were responsible for providing information to support all of these activities. You know, why does the bill of materials cost so much? What haven't we bought yet? Are we going to make our schedules? What are our risks, and what can we do to mitigate them? Many different aspects. So while these activities themselves are not necessarily system engineering, the results of system engineering supported at many levels of the program. And this also shows how the program management aspects of a large program integrate with the technical aspects, often through system engineering. Of course, requirements engineering is a major task on any large-scale system, but in DRIS it was actually minimized to some extent for a number of reasons. One of those was the integrated product team structure. We actually worked very closely with the customer. They were in regular daily meetings with us. So we were talking to them about requirements on a constant basis and understood the details of those requirements, so that we really didn't have to spend a lot of time writing down everything at a minute level. We had a good working relationship. And the team had domain knowledge. I mentioned that I had worked on censuses for 16 years. There's many people involved in this project who have been on censuses for nearly that long. So they understood the language of the census and understood, you know, what the terminology meant. There were still, I want to mention one other thing. We also used agile development techniques here. So again, many things were iterative, and we didn't need to do as much requirements analysis as is often done. There still were a large number of requirements to be managed, and there still were a lot of changes. That's one thing that's quite clear about the census is, as much experience as we have, things are going to change. Things change in the population, things change in politics, new form types need to be added. We had elimination of the internet option, which was originally proposed. What's called paper-based field operations was added late in the game. Changes in the telephone, questionnaire assistance, and coverage workloads occurred frequently. So there were changes that had to be managed. But requirements engineering was a major part of the system engineering work, but probably a little less than it is on many programs. I want to talk a little bit about modeling and simulation, which is something that we spent a lot of time doing. The basic process is straightforward, that you take assumptions and domain knowledge, use it to build various models, analytic models, simulation models, and use that to predict the quantities, the capacities, the timing, the results for your system design and for your system operations. Now, the real modeling and simulation in a system like this is a lot more complicated than that might make it seem. We had many, many hundreds of assumptions from our teammates who understood call centers, from the customer who understood the profiles they would expect in the response for the census, from ourselves at Lockheed, who'd done paper processing before and understood the characteristics of our systems. Excuse me. We took that information, combined it together into a number of different models. The discrete event simulation model was actually a true Monte Carlo type simulation to look at things, dynamic characteristics, such as what's the latency, how long does a form take to go through the system, what's the profile of that, and used it to validate some of our other models. One of our main models was the integrated performance, capacity, and cost model that linked together the volume characteristics of the system with the processing capabilities of the people and machines that composed it, and predicted how many units we need, how many servers, workstations, operators, warehouse space, all that type of information. And I also mentioned contact centers. We employed quite a large number of agents depending on the phase of the operation. And that's a modeling activity that needs to be done based on things like average wait times, average length of call, the call arrival frequencies, and all that information. So the outcome of all of that was a number of different models that predicted, excuse me, what we needed for our telephone infrastructure, how many ports, how big the lines need to be, voice over IP circuits, all kinds of things like that, the number of call centers, the number of supervisors, how many elements in the bill of materials, which was quite large with servers, workstations, routers, switches, sorters, scanners, all types of components, and how big the data centers needed to be, how much room for servers, for storage, for parking lots, all kinds of things. So the modeling was quite an extensive activity, and it wasn't just done once. We actually started early in the phase of the system with the customer's requirements and volumetrics and our own experience, and built an initial baseline model based on the system design. That gave us the information for a development, what we call a BOM, or a bill of materials. Then based on the actual software design, the quality design, performance testing, the models were updated, were calibrated, as we say, to produce a dress rehearsal model and the needs for our dress rehearsal system. Then based on the dress rehearsal, which was done in 2008, it was a small-scale test of the operations and activities. We, again, calibrated the model for the production model, found out how things really worked in the real environment, and also took in some new requirements to produce the final bill of materials and operational plans for facilities and how many people we were going to hire. But it still didn't end there, because we didn't just build this system, we actually operated it for the Census Bureau. And we used our modeling to run that operation as well. Whenever things didn't quite work the way the model predicted, we had to find out why, figure out what the fixes were, and what it meant to the long-term production and delivery schedules of the system. Skip that. We also had to do a lot of capacity and risk analysis. This is a big issue in any system like this, especially something that has a deadline like the census does. The census has to be done on the census year. If you don't do it, not only have you failed to meet the mandates of the Constitution, it's also potentially a statistical problem because you're not collecting the data in the same way, making it difficult to assess it from year to year. So you want to make sure that it's going to work. But how do you do that? Common approach is add some contingency to the estimates. Add 10%, 20%, 50%, double it. Why do you do that? Well, okay, you do it to decrease your risk, but why 10%? Why double it? What's the justification for those numbers? Turns out they're just rules of thumb. There really isn't any justification. And it also leads to some significant over-engineering. If you take every factor that you're not sure about and double it, you're going to build a system that's much bigger than it needs to be, and you're probably going to build a system that's planning for everything to go wrong at the same time, which is unlikely to actually happen. So we actually use some statistical methods that view the average resource prediction to be a normal distribution, and then computed the standard deviation and played some games with the statistics to add or subtract standard deviations from that average to increase our risk. So we've actually figured out the expected normal and the standard deviation and built the system for 2 standard deviations off of that so that we would have basically a 90% probability that we had enough resources to do the job. I also want to mention data quality engineering. As I mentioned earlier, we need to produce accurate results. So we had a number of processes required there. One, of course, was measure the accuracy along the way. But the other thing was to ensure keying accuracy. We had a goal of 97%. Keyers can be variable. Some people have good days and bad days. Some people are great keyers. Some people are not. So we had to put in mechanisms to deal with accuracy of the keyers as well, and actually used something called AOQL, Average Outgoing Quality Limit, which is actually a process control technique to assess the quality and make adjustments in the data dynamically, basically reprocessed keyers work if they were not making the objective. Also did near real-time analysis of the captured data using some analysis tools, particularly the Space-Time Research Supercross, which is kind of like a high-performance spreadsheet to analyze very specific pockets of data that were happening, say, by language or geography that weren't obvious in the system, and did independent verification of all of that. And I'll also mention the person who actually ran this or designed and ran this operation is also one of the instructors here at UMBC. Talk quickly about facilities. We obviously had lots of servers. One of the big problems we have is power and heating, ventilation, and air conditioning, as they say. Current server technology packs a lot of power in a small space. Dual quad-core processors fitting in a rack that's only 1 3/4 inches high, taking 850 watts of power. When you pack those into a rack of 42 units, you end up with a pretty high power requirement, 37.5 kilowatts per rack. That is about 70% of what the average house uses in a day, and it's just for one rack. That's about 18 inches wide. So this can get extreme. When we started to do these kinds of design, my construction people told me I'd actually have a hurricane in the server room, literally, because they needed to move the air so fast to get the heat out that it wasn't going to be practical. So again, we had to go make some design changes, spread things out a little bit, limit the amount of servers in a rack to get it under control. This is actually a diagram of one of the facilities, just quickly showing the areas where system engineering got involved. Now, we didn't draw this diagram. We had construction engineers actually do that, but they needed to know information to do that. They needed to know how big did the servers room need to be, how many servers, how many racks, equipment, total power, etc. They needed to know how many operators, workstations, so that we could determine workspace licenses, locker rooms, break areas, even toilets, which is usually required by local statutes. Storage for paper forms, how many we're going to have peak on average. Training, what was the expected attrition rates, flow of people, so we can size training and staffing and hiring areas. And of course communications, network drops, distance constraints, where are the switches going. So all of this really came out of my system engineers, and those numbers went into the facilities engineering people so that they could come up with the ultimate facilities design. I want to talk a little bit about interface engineering. This is another area where system engineers spend a lot of time. DRIS originally had, I think it's about 14 interfaces defined to major elements within the Census Bureau. That's kind of a large number, but not unmanageable. But the actual total, as it evolved over time, was much higher. I think we were up at like 42 different interfaces by the time we actually implemented the system. Each of these had to have interface control documents, not just defining what the specific character or performance elements of the interface were, but how frequently, what the data was used for, the format, the transmission protocols, all these characteristics so that you could actually implement these things and make sure they were right. And then there was, of course, the implementation and testing. Testing of the software, testing with simulators, doing what we call sneakernet, getting the data from the source, trying it in our software to make sure we're all agreeing on formats, and then the real live communications, actually running it over the wires through external communications interface, which is a non-trivial activity, but the final thing in your testing. There was another step. With that many interfaces, you needed to monitor those things during live operations to make sure they didn't fail, they're producing the right data, and making sure that you're actually getting the job done. So, results. How did it all work out? Well, in terms of our great little performance peak graph, we did make all of our dates. Our zero backlog date occurred as required. Our mailback backlog was processed by the end of May as necessary. The final delivery to the Census Bureau was made by the early September, as was required. Productivity numbers of our equipment and people either met or exceeded expectations, particularly the sorters, which was one of the trickier areas. They were a new sorter design. They met and exceeded actually the planned throughput of 20,000 letters per hour. The scanners, also a touchy area, physically scanning all that paper, made its planned throughput of 2.5 million forms per day, various form sizes. That was really pushing it. We just barely made that, but we did do it and even managed to exceed it in some critical areas. The keying operations actually exceeded requirements. We had planned on them processing what's called key depressions per hour, how many letters you can type per hour. 5,400 was the target. They actually achieved 6,800. A lot of that was the economy. The unemployment rate was high, which meant you had a lot of relatively skilled people available. This was a temporary job, so they were glad to take it and make some money while they were trying to get a more permanent job elsewhere. And the automatic recognition of our system actually exceeded expectations. We had expected to recognize 80% actually of the handwritten data automatically and not required people to key it. It actually achieved just over 85%. And accuracy, which is one of the key measures, exceeded requirements in all areas. The keyers turned out to be more accurate than planned. The optical character recognition exceeded the 99% accuracy. The optical mark recognition exceeded its requirements as well. And as a result, the overall output of the census data that we provide to the Census Bureau was 99.28% accurate, which is more than what they'd expected and more than what they'd achieved in the past. Some important practices from an SE standpoint: customer collaboration. The integrated product teams working closely with the customer, being able to ask them questions directly, talking daily with the customer was really a benefit here. These systems are too complex to completely define in terms of a fixed set of requirements in advance, and too many dynamic elements change during the evolution of the census for that to work. So we had very well-defined joint management structures, minimizing miscommunication and make everything much more efficient. Extensive modeling. I just touched on modeling in this presentation, but this system in particular, too large and complex to test at the full scale. I can't run an entire census with 300 million plus people just to test the system out. I only get one shot at it. So you have to do extensive modeling to try to test the system in the lab and extrapolate that and know you can extrapolate it and make it work. Modeling is really necessary to project the performance and project the reliability and the characteristics of the system. It's also got to start very early and evolve and not be done at the last minute. And we use those models as the basis for operational analytics and management, which was key to actually making this run. Also, active interface management. That wasn't something we've done at this level in the past, but there were so many interfaces here to so many different parties that we needed to have operational management of the interfaces to make sure they were working as required and get the focus on fixing them when they weren't. And overall, system engineering is really the key to program success. It's not hardware development, it's not software development, it's really the thing that links all those together, and without system engineering you're not going to make the numbers and be successful. So it's not just me identifying the success. A few months ago a report came by my desk from the GAO. They put out a report on critical success factors underlying major successful system acquisitions. And interestingly enough, the DRIS system from the Commerce Department was one of the 9 programs that they highlighted. And you can see, if you could read it, you can always get the presentation here, many of the critical success factors were the things I was talking about: working with the customer, understanding the requirements, staff being consistent and knowledgeable, and DRIS had many of these characteristics. I just want to end with, it really is about people. This is just a group of people, the leadership team for DRIS, but it took many, many more people to make DRIS successful. The development team was on the order of 300 people from a number of major companies at one point in time. The operations activity actually employed 15,000 people at its peak in those various telephone and data centers across the country. So it really takes a lot of people to make it work, and system engineering is really a team activity. So with that, I will turn it over to Ted for any questions we may have.
Well, Fred, that was really impressive. You know, I knew that you did this, but I had never seen the scope and the quality of the program before, and really glad to see it, and pretty proud too. The audience hasn't sent in any questions, but I have a few myself. One is, you mentioned that you eliminated the internet option. I'm just curious, why did you do that? Was that a political decision or a technical decision or what?
It was a decision by the Census Bureau, and it was made on technical merits, I shall say. They had done surveys that basically determined that while the internet is a good response channel, it's accurate, it's cost effective, the people that will use the internet are the people that will respond on paper. And since it's really all about getting the response, there wasn't a lot of response advantage to the internet. They would have gotten those responses anyway. However, the internet is a security risk. The U.S. is a big internet target from people around the world. And so when you look at the risk that the internet would introduce to the system of people hacking in or people disrupting the census versus the benefit, which seems marginal because you're going to get those responses no matter what, they made the decision not to go with the internet. We have done the internet in Canada and the UK. It is a viable activity, but the security aspects of it in the post 9/11 world have to be considered strongly in doing it.
Good explanation. Another question occurred to me is, you know, IT is progressing pretty fast. So how does how you did it this time compare with how you did it 10 years ago, or, and I don't know who, I know Lockheed Martin had the program 10 years ago, but what about 20 and 30 years ago?
Well, it's actually evolved over the years, and IT has been a lot of that evolution. If you look back at the censuses that were done, I believe prior to 1970, they were basically done by enumerators going door to door with pads of paper, collecting information. So it was all paper and pencil, shall we say. In the 70s and 80s, they introduced optical character reading, or actually optical mark reading technology, where they pretty much had you fill in boxes and shined a light through paper and detected whether the box was filled in. So they started to automate the collection of data. I believe the Bureau actually did some automated data collection in 1990, but 2000 was actually the first year where the optical reading technology was sophisticated enough to get pretty accurate and high volume results from the processing. So they started to use that as a cost saving mechanism. That technology has evolved to become, as you can see, very accurate, very ubiquitous for both optical mark and optical character reading. In addition, the processing capabilities of the computer systems have increased, exponentially. And we've gone, actually in this census, one of the big differences is we captured all the forms in color. That obviously creates a larger volume of information, but it gives you more information. So if you mark that checkbox with a blue pen and it's got a black background, I can tell the difference. I can tell what the mark is very definitively. I couldn't do that in black and white because it would both look black. So that's one of the innovations that was added as a result of the ability to have the computer resources to do it, because it takes a lot more computer resources. So we have evolved the sophistication. The databases have gotten bigger and more complex. We constantly collect more management information so we can do these things more effectively. So that's what we're doing with a lot of the IT technology. And of course, the internet now is becoming more of, as well as actually telephone operations are becoming more viable Automatic call direction technology makes telephone more efficient. The internet is now ubiquitous. Obviously wasn't back in 1970. I don't think hardly anybody even knew what it was back in 1970. So we've been using technology across the years to make this more accurate, more efficient, more reliable, and ultimately we're probably going to be using it to make it less expensive as the technology continues to evolve.
Thanks. Turns out there are some questions have come in now from the audience. I'd like to read a couple of those to you. How many languages were represented, and how difficult was it to include these languages in the testing phase?
It's a good question. The two primary languages were, of course, English and Spanish, and we don't actually treat Spanish as a foreign language. We treat it as a legitimate language like English and process it exactly the same way. There were specialized forms for a select set of other languages that were used in various testing phases, but the Bureau does quite extensive analysis into what languages are being used in the country, what frequency they're being used, and then therefore how to support them. I'm sure there are thousands of languages used, and designing a form for every language really is not practical and for the most part not necessary. So they also used language guides for many of these, and we also use translators in certain cases, where some of the forms, for example, one of the forms was actually you could respond in Russian, Cyrillic. And we'd send those out to a translator that would translate that into the English equivalent so that we could capture it and have the data all normalized. Another one was Chinese, of course.
Mm-hmm.
So basically, those were used in the tests and in the final operation, but there's a number of different techniques that get used to address the various language needs of the population.
Thanks. I see a question here about Canada. The fact that they did use the internet. How was the data pulled over the internet in Canada specifically?
How was it pulled over the internet?
Well, how did they use it? How did you use the internet in Canada? I don't.
Oh,
you know,
that's true. They had an interesting approach in Canada because what they did is they actually did not send you a form right away. They sent you a postcard that said, "Please respond to the census. Here's your internet ID." And the idea was to encourage people to use the internet because it is a better mechanism if you can get the response that way. And then if you didn't respond, they sent you another one, and if you still didn't respond, they actually sent you a paper form. So they had an internet ID. You could log into the internet effectively, get the form, fill it out, submit your results, and it got brought into the system and merged with the other data from the paper forms. It was very successful in Canada because of what they called their internet-first approach. I don't remember the exact numbers, but it was greater than 40% of the responses, I believe, were actually done on the internet in Canada. So we'll probably see internet in the U.S. In the future. It has been used in other countries. But, you know, it is about getting the response from everybody, and everybody doesn't really have the internet. You got to think of people that are homeless, people that are in, say, nursing homes that probably aren't using the internet. And we want the responses from those people as well. So paper will not go away, but internet is a more effective response mechanism for those that are well connected.
Mm-hmm. Here's another question. How does the DRIS system and its complexity compare with the census systems you built for other countries?
You know, they're probably pretty close. They have differences. The biggest thing with DRIS is volume. The volume of forms in the population of the U.S., 310 million people. That's bigger than the UK or Canada. I didn't build the census for India and China. Those would actually be bigger. So that's where most of the complexity comes from. But there are different measures of complexity. For example, in both the UK and Canada, they ask a lot more questions on the form. So it turns out if you want to look at it as a measure, in terms of the number of pages of paper that the system had to process, the UK actually processed the same number of pages as the US. The reason is they had a 32-page form instead of effectively a 6-page form in the US. They asked a lot more questions. So what they lacked in population, they made up for in volume of questions. So there are aspects there. There are some processes we did in the UK and Canada that we didn't do in the US, but you know, they're roughly equivalent, I would say. But there are many different ways to measure that, and you know, the answers come up higher or lower depending on which measurements you use.
Mm-hmm. Thanks. Here's one. Well, are expatriates included in the totals? And if so, how difficult is it to capture them?
Yes, they are. I believe they are. I know there are countings of people on ships, people in embassies in foreign countries. You are counted if you are a U.S. citizen, and of course your location is counted. People in the military bases in particular, all that gets counted, but they are dealt with in a different way than the normal population for a number of reasons.
Mm-hmm. What was the overall response rate, and how did you extrapolate for the total population?
That's really something more the Census Bureau does. I believe the response rate to the mailback was approximately 73%. And then, of course, the Census Bureau went out and enumerated the rest of the people. Now, their objective is to count everyone, so they made quite an effort to get everyone in the country. And then they actually do a survey to find out how good they did. They do a coverage survey that goes out and resurveys about a 1% sample of the country and compare the data. And from that, you can estimate how many people we missed. And that number is usually very small, on the order of tenths of a percent. And so they try very hard to count everybody once and in the right place, as we said.
There's a couple more questions here, but we're running out of time, and there's one I'd like to ask as moderator, and that is, what are the characteristics that you look for in a good systems engineer? Because clearly you have to use lots of them, and you've seen lots of them in addition to being one yourself.
It's a good question. The major characteristic I look for is actually curiosity. System engineering is a very diverse activity. It involves a lot of different specialties and linking together the various engineering elements within the production of complex system. And I find that the best systems engineers are the ones that are curious about just about everything, because they're going to have to research topics they probably never dreamed of before in order to come up with some of the answers we're looking for. So they're going to have to be interested in lots of different things. In addition to that, they need to have some good skills in mathematics, in various engineering sciences, because a lot of this job, at least my experience, is mathematical in nature. Not that you have to have a doctorate in mathematics, but you can't be afraid to use spreadsheets and do calculations, because boy, we do a lot of that. And of course, modeling skills are also key, because we do a lot of modeling to predict the various things that we're trying to build.
Thanks for all of those answers and for the presentation, Fred. I think we need to stop here because we promised people we would stop in an hour. I want to just thank the audience and encourage you to give us some feedback. We'd appreciate if you would complete the survey at the end of the presentation so we can continue to improve webinars like these and see what we need to do for the future. Again, remind the audience that the recorded webinar will be available in a few days on both of the websites, and also to invite you to on-campus information sessions for both of the programs coming up. 12:30 to 1:30 session on engineering management here on campus, and the Information Technology and Engineering, the ITE building, room 456 on April 18th. And then on April 30th, Monday, April 30th, there will be one on systems engineering from noon until 1. And will be at the UMBC South Campus, which is off Rolling Road. the main seminar room on the first floor. And you can see there that we would encourage your giving us your intent at the umbc.edu/RSVP website. Again, thank you, all of you, for attending. I think it was a wonderful experience. And Fred, thanks again for not only giving us a great webinar, but for being an outstanding instructor for the capstone course, the System Engineering Project course. Thank you and good day.
Thanks.